Hey learners, welcome back. Today we are going to break down how Kubernetes security actually works as layers. Kubernetes security isn't just a single setting that you turn on. It's 5 layers stacked together with each one protecting against risk that the layer below it cannot. Skip one and the layers above it becomes much easier to compromise. This is also helpful if you're preparing for the CKS, aka Certified Kubernetes Security Certification, since understanding the security layer is the core part of the exam. By the end of this video, you'll understand all the 5 layers, what each one does, where default configurations leaves you exposed, and how to secure them. One quick note before we begin. Thanks to Teleport for sponsoring today's video. Later on, I'll show you how it helps to set up secure access to Kubernetes clusters and your infrastructure. Let's dive in. Layer 1. Secrets. It all starts with how you store data in Kubernetes. There are 2 objects that people use and the difference matters here. A config map holds non-sensitive config such as URLs, feature flags, and settings. It is stored as plain text in the etcd database. That's fine. That's what it's for. The mistake here is putting sensitive values in config map. Now imagine your database password is sitting in etcd in plain text with nothing protecting it. That's not right. A secret, on the other hand, is meant for sensitive stuff. But here's where most people get wrong. A secret isn't encrypted by default before the information is stored in etcd. Kubernetes simply base 64 encodes the value. That's not encryption. Anyone who can access the data can decode it in one command. And the critical part here is both config maps and secrets live in etcd. So anyone with access to etcd data, backups, or sufficient Kubernetes permissions can read them. Now, to secure this layer, you need to do 3 things. Number 1, put sensitive data in secrets, never in config maps. Number 2, turn on encryption at rest and back it up by KMS. Now, those who don't know about KMS, it's a key management service, often backed by a cloud provider, where the provider takes care of generating, rotating, and managing your cryptographic keys. So, in this case, your key lives outside the cluster. Number 3, for anything that's truly sensitive, keep it outside etcd entirely. Store it in external secret managers, often backed by different cloud providers, and just pull it during runtime. And also lock down RBAC so that only few identities can read these secrets. That's layer 1. It protects data that's sitting still. This layer says nothing about who can move around inside the cluster. That's where we go to layer 2. Your network. By default, Kubernetes networking is wide open. Every pod can talk to every other pod across every namespace. So there are no walls. That's fine until one pod is compromised, because from there, an attacker can reach everything else. You close this gap with Kubernetes network policies. By default, you block all traffic first and allow only the connections you need. Front end to back end to database, nothing else. But network policy is just a rule. Something has to enforce it. That's your CNI, aka Container Network Interface, your networking plugin. And one important detail here is, if your CNI doesn't support network policies, your rules cannot do anything. A simple example to visualize this is a pod getting compromised because of a bad dependency. On the open network, it connects directly to your database. With a network policy enforced, that connection is refused. This is why plugins like Cilium comes in, and a lot of teams use it. Before Cilium, Kubernetes network policies were typically enforced using IP tables, which, as the name suggests, relied heavily on IP addresses and rule tables that became very difficult to manage and scale. Now, what does Cilium does differently? It uses eBPF, a module, to enforce these network policies inside the Linux kernel, and it is based on workload identity, not just IPs. Hence, that makes policy enforcement more faster, more scalable, and observable. In summary, it lets you run small programs inside the Linux kernel, which is the core of the OS, also without touching the kernel code itself. So it's very secure. So for this layer, do check what CNI plugin you are using, because that decides the security posture of this layer. And as discussed, Cilium is faster at scale. It lets you enforce policies based on identity and even HTTP paths, not just IP and ports. That's layer 2. You control which pods can talk, but not whether the traffic can be read. Now let's jump to layer 3, your traffic. There are 2 types of traffic in Kubernetes: north-south traffic and east-west traffic. North-south traffic is traffic coming into or leaving your cluster. For example, when a user opens your application through a browser, the client sends a request to an internal system backed by your load balancer, CDN, and your backend Kubernetes cluster. Now, this traffic is typically protected by TLS at the ingress layer. So the data is encrypted between your client and the cluster. On the other hand, east-west is the traffic within your cluster, pod to pod and service to service communications. Now here's a common point of confusion. The Kubernetes control plane is already encrypted by default. Communication between components and API server and between API server and HCD uses TLS by default. What isn't encrypted by default is your application's east-west traffic. People often assume that if it's inside the cluster, it is safe, but it isn't. If someone can intercept the traffic inside the cluster, they can read the data. This is where mutual TLS, aka mTLS, comes in. In this case, every service gets an identity and every connection is encrypted and authenticated. So every service verifies the identity of the other service before exchanging data. A service mesh like Istio or Linkerd can handle this automatically. And if you're already using Cilium, it can encrypt pod-to-pod traffic. As a simple example, imagine your authentication service is sending tokens to another service. Without encryption, anyone who can observe the traffic can read those tokens. With mTLS enabled, the traffic is encrypted and unreadable. So far, we have covered data security, network security, and traffic security. Together, these layers protect the cluster itself. But in most Kubernetes environments, the biggest risk isn't the system. It's someone who already has access. That's where layer 4 begins, your access. How do people actually connect to the cluster? In most teams, it's a kubeconfig file. This file holds the certificate or a token which usually doesn't expire, and it gets copied onto laptops, pasted to Slack, and even your CI pipelines. At some point, nobody knows how many copies are out there. If someone leaves the team, you rotate the credentials and hope that you caught every copy. The root problem here is the permanent credential. Instead of giving someone a file they can carry forever, you tie their access to identity. Now, how can you do that? You authenticate through your existing SSO. This could be Google, Okta, whatever you already use. The user receives a short-lived certificate, and whenever the certificate expires, so does your access. So no permanent credentials to rotate or chase down. One way to implement this is to use a platform like Teleport. It acts as an identity-aware access layer across your infrastructure. You start by signing in with your corporate identity provider. Once you're authenticated, Teleport automatically issues you a short-lived certificate, so you never have to manage a permanent kubeconfig. Inside the dashboard, you immediately see every resource that you have access to, from Kubernetes clusters to servers to internal applications and cloud resources. And when you open a Kubernetes cluster, you can connect to it immediately. Your Kubernetes permissions come directly from that short-lived identity, so there are no static credentials stored on your laptop, and you don't even require VPN here. Now here's the key part. If your certificate expires or if your access is removed from your identity provider, you simply can't connect until you authenticate again. For example, if an engineer leaves the company, disabling their SSO account immediately prevents new access. There's nothing left to rotate or clean up. So the gist of this layer is to protect your Kubernetes environment from people who can get in and access your resources. Now, so far we have been talking about human identities, but same principles applies to machines and workloads, your CI/CD pipelines, your AI agents, your microservices. So instead of storing short-lived secrets, they authenticate and receive short-lived certificates by Teleport so they can access resources they need. This way, if a credential is ever compromised, its lifetime is limited instead of persistent access. Now, the last layer is what happens once they are inside. Layer 5 is all about your pod or workload security. In this layer, we focus on protecting what's actually running inside your cluster, and if we know if something goes wrong. Let's start with a problem that most people don't think about. When a container starts, by default, it runs as root. This means if someone compromises your container, they are already running with the highest level of privilege. Now, you can reduce that risk with a few simple settings. First, run the container as a non-root user. Second, remove all the unnecessary Linux capabilities. And third, make the file system read-only. Then enforce these policies across every pod so that insecure workloads never get deployed in the first place. Now, this only protects with workloads you have planned for. It doesn't help if something unexpected happens at runtime. A new process starts, a sensitive file gets accessed, or a workload starts communicating with an unfamiliar destination. Now, apart from the system-based risk, there's also the human side for this layer. When someone opens an interactive shell inside a running pod, They're operating directly with a live environment. Think of it as a new engineer inside a live environment with no guardrails. Sounds so risky. Without visibility, most teams have no record what happened in that session or which engineer is responsible. Now you need a platform to monitor these sessions. Teleport, for instance, provide this record with detailed audit logs that attribute every action to a verified cryptographic identity. These identities are automatically issued to every engineer, CI/CD workload, AI agents, and service accounts that's interacting with your infrastructure. Let me show you. Here in the audit log, every privileged action is tied to a verified identity. You can see who connected, when they connected, and exactly which Kubernetes resource they accessed. Now, if someone execs into your pod or runs some kubectl command, it's recorded as a structured audit event, and it can also be forwarded to your SIEM for further analysis. Now, as we open one of the recorded sessions and click play, instead of just reading a log entry, you can replay the entire terminal session exactly as it happened. Every command, every output, all attributed to the engineer who performed it. This gives you a complete audit trail for your security investigations, compliance, and troubleshooting. So this layer comes down to 3 things: log down what runs, watch what happens, and record who did it. Now let's wrap up. Layer 1 is your secrets or your data layer. It should be encrypted, not just encoded, and it should never be in config map. Layer 2, your network. It should be closed by default and enforced in kernel with CNI plugins like Cilium. Layer 3, your traffic. The control plane's already on TLS. You add mTLS for the rest. Layer 4, your access. It should be short-lived and tied to your identity. Layer 5, your pods and workloads. It should be hardened, watched at runtime, and every session should be recorded. 5 layers, each one covering what the others can't. Thanks to Teleport for sponsoring this one. If you want identity-based access and session recordings for your clusters without managing kubeconfigs by hand, definitely check them out. Link is in the description below. That's it for today. See you in the next one.